Electronegativity and bond polarity. And if we remember in Chem 1 and in Chem 2, we probably discussed electronegativity and whether molecules polar or nonpolar. So what we're interested in looking at is when electrons are shared equally, it is said to be nonpolar, covalent bond. So between carbons, they're going to be shared equally for our bond. That will always be a nonpolar covalent bond. When electrons are shared unequally, there's an unequal sharing of electrons that are bonded, and it's nonmetal, it is said to be a polar covalent bond. So where we're going to go with this is, where do we look to find out whether they're going to be shared equally or unequally? So where we get this information? So hydrogen, H2, are shared equally. Because it's an s orbital overlapping with an s orbital for starters. They're going to be shared equally. Or if I have a carbon to a fluoride, the electrons are going to be closer to the fluoride than they will be to the carbon. That's going to give this fluoride a slight negative charge. It's a delta. And this carbon is going to have a slight positive charge. And we use this arrow called a dipole moment to show the direction of the electrons. In other words, if you look at the arrow is pointing towards the fluoride, which means then the electrons will be closer to the fluoride than the carbon. That is, like I said, is known as a dipole moment. It is given the symbol mu. So how did we know that they're there? And how we know that is based upon electronegativity. So we use electronegativity to guide us in making these predictions, whether a bond will be polar or nonpolar. So using the periodic table, and I just put part of the periodic table up there, we use what is known as the Pauli scale, where fluoride is the most electronegative. It has a scale of 4, where carbon is 2.5, which means the fluoride is going to pull the electrons towards it. And we can use this scale as a model. So if you remember right in your periodic table, my version of the periodic table, we say electronegativity increases as you go to the right, and we can see that. And it increases as you go up. And we can see that here, 2.6 to 3.4. We can see that it does increase, so electronegativity trend. So, can we then predict the direction of the dipole moment for the following? So here we have carbon. It was 2.5, Chloride is 3.2, which means chlorine's more electronegative. So the dipole moment, the electrons are going to be pulled closer to the chlorine than they will be to the carbon. So if we have a carbon-oxygen bond, carbon is still 2.5. Oxygen is 3.4. The electrons are going to be pulled closer to the oxygen. Oh, and I forgot, remember when they're pulled that direction, that means that chloride, is going to be slight negative. And that's going to make the carbon a slight positive. Oxygen's going to be a slight negative. Carbon's a slight positive. So if we do this next one down here, nitrogen and sulfur. Nitrogen is 3.0. Sulfur is 2.6. They're pretty close. But there will be a... Okay, my pencil just disappeared. The nitrogen is going to have a slight pull, giving it a slight negative charge, and the sulfur then a slight positive charge. If we did the carbon and the sulfur, we had 2.5 and a 2.6. It is pretty much a wash. This one, nitrogen and sulfur, is close to a wash. So, formal charge. First of all, we want to look at this molecule. This is formaldehyde. We already know that oxygen's going to have a slight negative charge and carbon's going to have a slight positive charge. These are not considered formal charges. These are real charges. Or should I say partial charges? They do exist because of polarity. So a formal charge just provides us a method of keeping track of electrons. It'll also help us on some other things too, eventually. So if we have, and I have my method of doing formal charge. So if we have oxygen, well, we have the hydronium ion. I have a method that I use, available electrons. Let's go valence. Valence electrons. And we're going to do this for oxygen. Oxygen has 6 valence electrons. Where do I get that? It's in column 6 of the periodic table. So now, the books usually provide a mathematical model. That's too complicated. So I do what I call my scissor method. So any bond, I just cut it in two with scissors. So now, how many electrons around it? We count. There's 1, 2, 3, 4, 5. 5 electrons. Then we just subtract, and it's plus 1. So it is plus 1. So remember in Chem 1 and Chem 2, you wrote hydronium ion and it has a positive charge. And this is why. So let's do this molecule. So we'll do carbon and nitrogen. So carbon has how many valence electrons? Periodic table, it's in the column 4. Nitrogen has how many valence electrons? It's in row 5. So now when I get my scissors out and I just cut there, cut every bond. Now we count around the carbons. There's 1, 2, 3, 4. We then subtract 4 because that's how many is around it. And we get 0. Nitrogen we count. 1, 2, 3, 4. We subtract 4. We get a +1. So with this molecule, for tracking the electrons, we can say it has a full positive charge. Not a slight one, but a full positive charge. So some common bonding patterns that you need to be familiar with. So with carbon, if we have 4 bonds or 8 pairs of electrons around it, that has no charge. If it loses a pair of electrons, it becomes positive. And in this case, this is a carbocation. So the next one here, it has 3 bonds, but it also has electron pair that are not bonded. This is a carbanion. So nitrogen, in its normal state, neutral position, it's going to have 3 bonds and 1 electron pair. When it then develops 4 bonds, and it can pick up a proton or some positive charged species, it's now going to become positive charged. If it loses a bond but leaves the electrons, then it becomes negative charged. So with our oxygen, oxygen normally has 6 valence electrons. It will normally have 2 bonds and 2 pairs of electrons in its neutral state. If it picks up a bond, it becomes positive. If it loses a bond, so now it has 6 lone pair of electrons, or 3 pairs of electrons around it, it is now negative. This is a pattern that you're going to see over and over and over again. So you need to be very familiar with this. Because it's going to help us with ionic structures. So here I have a molecule, CH3, NH3 with a positive charge. How do I know the nitrogen has a positive charge? When I draw the Lewis dot structure, I see that the nitrogen has 4 bonds. Nitrogen normally has 3 bonds and 1 electron pair, so that is why the nitrogen's positive. And then there's a chloride ion, so this would be an ionic structure here. The attraction between the positive and negative make an ionic compound, ionic structure. Do not draw it this method, because if you did, and I'm making a mess, nitrogen has 10 total electrons around it. That is impossible. So let's say we have this molecule here, sodium acetate. This is the correct ionic structure. Represents there's an ionic bond here between the oxygen and the sodium. And since oxygen normally has what? 2 bonds and 2 electron pairs. For neutral, now it has 1 bond and 3 electron pairs. It is negative. And it can be attracted then to a sodium for an ionic structure. It is not a true chemical bond. I hate to say that. It is not bonded together as I have drawn here. It is an electrostatic attraction. This is incorrect. Does not necessarily, as you draw it that way, it represents a covalent bond. So what we're going to find out is here in a little bit that electrons can move, etc. So if I have, I'm just trying to think of it. And it can be attracted to a potassium ion. The molecule, this part of the molecule is covalent, but it is considered ionic structure because of the potassium and the oxide are attracted to each other electrostatically.